Good day everyone. This project focuses on reducing flip chip packaging defects using the DMAIC methodology at Intel's Penang. Flip chip packaging is one of the most critical processes in semiconductor manufacturing because it directly affects product reliability and production yield. However, packaging defects such as shoulder bridging, voice misalignment, and open shoulder joint still occur and contribute to higher production costs and customer dissatisfaction. Therefore, the objective of this project is to identify the main causes of this defect, analyze the project variable influencing defects rates, and propose improvement strategy using the DMAIC approach. Successfully reducing defects will improve product quality, manufacturing efficiency, and overall customer satisfaction. The literature review identified several factors contributing to flip chip packaging defects. Among these, the reflow temperature profile is consistently reported as the most significant process parameter. Previous studies show that the operating below the optimal temperature can result in incomplete shoulder melting and open joint, while excessive temperature may cause oxidation, package wall patch, and increase defect rate. As illustrated in Figure 2.2, the defects rate decrease as the peer reflow temperature approaches the optimal range of 245 to 250 degrees Celsius before increasing again at higher temperature. In addition to temperature control, the researchers recommend regular equipment calibration, moisture control, statistical process control, and operator training to minimize defects and improve manufacturing performance.
Right, so for the analysis phase, right, our objective is to identify the root cause of the high defect rate in the flip chip packaging process in Intel. So first we use the fishbone diagram to explore all the possibility causes under the 6 categories, which are machine, method, material, manpower, measurement, and environment. So for this analysis, we can see that several issues were identified. For example, like reflow oven miscalibration, lack of standard operating procedure, insufficient monitoring and operating training gaps. So after we evaluate all these factors, we found that the most significant contributors was the inconsistent reflow oven temperature profile. So this is very important because it directly affects the solder joint quality and increase the defect rate. So after we identify the potential cause, right, so we need to further validate which one is the root cause of the problem, and we using the firewall analysis and Pareto analysis lah. So the firewall analysis actually helps us to track the problem step by step, and we found that the temperature inconsistency was mainly caused by the absence of a standard calibration procedure and inadequate preventive maintenance practice. So when coming to the Pareto analysis, we use it to determine which defect contributes the most to the overall defect rate, and we can see from the diagram the results show that the solder void formation accounted for 42% of defect, while incomplete solder melting contributed another 30%. So together, two of these methods, we found that the main issue is the temperature control, and that is the issue that we need to address. So we need to improve. So there is a several corrective actions that we implemented. So this includes the optimizing the temperature profile by using design of experience, introducing real-time temperature monitoring, standardizing operating procedures, and establish a preventive maintenance schedules. So to ensure that all these improvement was sustained, we also use control measure. For example, we always monitoring, we let our operator have certifications, and then regular collaboration activities. And as a result, the defect rate was successfully reduced from 5% to 2%, and we saw that from the process capability index, it is improved from 0.72 to 1.15. So it showed that it's more stable. So overall, the DMAIC cycle approach successfully improved the product quality and process performance.
This slide explains the define and measurement phase of DMAIC methodology used at Intel Penang assembly and test. In the define phase, the main problem identified was the higher defect rate in the chip packaging process. The defect rate for around 5%, which accepted for the company quality target of less than 3%. This defect caused the scrap rework and production delay, and also increased the manufacturing cost. Therefore, the project objective was to reduce the defect rate from 5% to below 3% and improve the overall production quality. The project scope focused only on the reflow soldering process because quality reports show that many defects occur during the soldering joint formatting. Key factor involved include the temperature setting, heating profilers, equipment performance, and operation compliance with the standard operation process. SIPOC analysis was also conducted. The supply included water, wafer, substrate, and soldering material supply. Input the consists of silicon wafer, soldering bump, and machine setting. The process flow for plug application, chip replacement, reflow soldering in inspection and underfill. The output is complete fit chip semiconductor packaging while the customer are Intel testing department and OEM customer. In the measurement phase, the current process performance was evaluated. Results show a defect rate of 5% and production yield of 35%, which was below target of more than 97%. The process capability value CP of 0.85 and CPK of 0.72 indicate that process was not capable in consistent meeting quality requirement. Data was collected from AOI system, X-ray inspection, SPC record, maintenance log, and final testing report to support the further analysis and improve the activity.
Today I will present about the conclusion and suggestions of our quality improvement project at Intel Corporation Penang Assembly and Test. First, our study successfully demonstrated that the DMAIC methodology is an effective approach for improving quality performance in semiconductor manufacturing. Through the define, measure, analyze, improve, and control phases, we identify the main root cause of defects in the flip chip packaging process, which was the inconsistent reflow over temperature profile. Using quality tools such as the fishbone diagram, Pareto analysis, 5 Whys, SPC, and DOE, we develop effective improvement solutions. As a result, the defect rate was successfully reduced from 5% to 2%. Product yield increased from 95% to 98%, and production scrap costs were reduced by approximately 30%. These improvements enhance process stability, product quality, operational efficiency, customer satisfaction, and strengthen Intel Penang's competitiveness in the global semiconductor industry. Moving on to suggestions. First, Intel Penang should expand the application of DMAIC to other critical manufacturing processes to further improve quality and reduce variability. Second, the company should invest in AI-based inspection systems and advanced automation technologies to improve defect detection accuracy and support near-zero defect manufacturing. Third, implementing IoT-based predictive maintenance systems can help prevent equipment failures, reduce downtime, and improve process reliability. Fourth, Intel should continue strengthening employee competency through Six Sigma Green Belt and Black Belt training, technical development programs, and quality awareness initiatives. Finally, the company should integrate sustainability practices such as energy optimization and waste reduction into its quality management system to achieve both operational as well as environmental responsibility. In conclusion, continuous improvement, advanced technology adoption, employee development, and sustainable manufacturing practices are essential for Intel Penang to maintain its position as a world-class semiconductor manufacturing facility. Thank you.